I was going to tell one more Danzig story. So this one's also on duality. So when Danzig came up with linear programming and the simplex method, there was a big conference that they organized. It was organized by Charlie Koopmans, who actually was at the University of Chicago at the time. He won the Nobel Prize along with Kantorovich. Yeah. So Koopmans organized this conference, and he invited many famous people, including John von Neumann, who was, he great mathematician, but had also been the one who sort of worked on the original design of the ENIAC computer, the first kind of digital computer. And Oscar Morgenstern, who worked with von Neumann. So Danzig presented his work on linear programming, including duality. And Oscar Morgenstern said, well, what is this linear programming? Nothing in the world is linear. This is irrelevant. Linear doesn't have to do with anything. And then Danzig said, well, these are my assumptions. And then it kept on going, and he kept on interrupting Danzig and not letting Danzig talk. And then finally, von Neumann got up, and he said, look, the man said it's a linear program, and that's what his assumptions are, and so now you should shut up. And then later, von Neumann asked Danzig to come and explain this idea about dual. And then Danzig goes and he gives a personal lecture to von Neumann for about 45 minutes. And then afterwards, and Danzig's wondering because he's not asking many questions. And he's thinking, oh, maybe he's just totally lost. He doesn't understand. And then Danzig gets through going through all this about duality. And von Neumann says, oh, that's what you're talking about? I know all about that. The reason that von Neumann had sort of intuition for it is because you can think of the dual as a game against the primal. And so von Neumann thought of it in terms of games. Okay, that's my other Danzig story with von Neumann. Today what I'll talk about are chance constraints. So these are constraints that have to hold with a certain probability. So most of the time what we try to do in these chance constraint problems is to come up with an equivalent representation which is deterministic. So a way in which you can just write a set of constraints that will be the same as your chance constraints. So I'll talk about a couple of examples of that. There's an issue, and in fact there was a series of papers that sort of debated this issue, that some people say chance constrained programming violates principles of information theory. And so I'll give you the example. So I'll show you the example, and we can think about why it does or doesn't make sense. Sometimes chance constraint programmings end up with non-convex regions, so I'll talk about what happens or what you can do with non-convex regions. And then there's a way in which you can guarantee convex regions, and that's called this principle of quasi-concavity, so that the probability distributions are quasi-concave. So we'll talk about that. And then I'll mention a few things about approximations, how you can get guarantees with some samples, and how you can use these Boole-Bonferroni inequalities. This is basically inclusion-exclusion. So you include some sets, exclude some sets, and then come up with approximations of the chance constraints. Okay, so that's the agenda. All right, so the model I'll focus on, and this was originally called the P model by Charnes and Cooper. So the P model meaning that the P, the probability, is in the constraint. Sometimes they put the P in the objective and they call that the E model. So this is the P model, that it's in the constraint. So the idea here is that we're going to optimize an objective function in X. And now it's not that there's a recourse after we make our decision X, but the constraints aren't realized. So you might think of this as, I'm trying to satisfy some demand. I don't know what the demand is yet, but I have to order enough to satisfy the demand with a certain probability. So the probability that the amount that I order is greater than or equal to the amount that is demanded must be greater than or equal to this alpha. And it is expressed in different ways. This says that I have to do this independently for M1 different sets of constraints. So this might be that I have to satisfy demand for every week with a probability of, let's say, 95%. So it might be I satisfy the demand every week for with probability 95%. Now, the other thing you might say is, well, you could also satisfy the demand for the entire year with probability 95%. And that would be a joint chance constraint. That means I would put it all in here. So we either have separate chance constraints like this, or we could put them all inside and then say it's a joint chance constraint, all of whom have to be satisfied with a certain probability. Okay, so other examples would be like, yeah, the probability of a loss. I don't want to lose too much, or I set a lower bound on how much I'll lose in an investment, and the lower bound on the loss in the investment is at most 1 minus alpha. Yeah, as I say, sometimes they're separate and sometimes they're joint. Okay, so here's an example. So let's suppose we have an airline again. I like airline examples. So the airline has 200 seats. Again, 200 seats. It divides them into these 3 categories: first class, business class, and economy class. And then what the airline wants to do is it sets targets for what fraction of the demand it's able to satisfy. So it might say, I have to satisfy 98% of the first class demand and 95% of the business class demand. Now the business class demand, no, we don't care about the economy class. This is to get, yeah, you know, the business class tickets are like 6 times as much as economy class tickets. So they want to make sure that they get the business class and first class tickets. So the business class, however, you can always put a business class passenger in a first class seat, but you can't put a first class passenger in the business class seat. So, so you can upgrade the business class. So the business class could also use your first class seats if you have those seats available. Okay, so let's suppose that we have a normal distribution for the first class seats with a mean of 16 and a variance of 16. And the business class has a mean of 30 and a variance of 48. 16, yeah. Yeah, so let's say, so this means the average is 16 and the variance is 16. So the standard deviation is 4. And then this one, the average is 30 and the variance is 48. The reason it's 48 is because 48 plus 16 is 64, which we'll see in a minute. So then I can take the square root. Okay, so we have these two, and I'm going to assume that they're independent. So this would be the first class demand. This is the business class demand. And now the constraints are that the probability that this would be the number of first class seats. The probability that the first class seats exceed the demand, in other words, that the demand is less than or equal to the number of seats, has to be at least 98%. And then, since it's the business class passengers, that's the business class passengers, that's CB. Since they could also take the business class seats as well as the first class seats, the probability that the seats in both categories is greater than or equal to the demand in both categories is at least 95%. Okay, so what we'd like to do is to take these constraints. We have these two constraints and turn them into a set of deterministic inequalities. Okay, so the first one's relatively easy because it's just saying, you look at, this is just saying, oh, this is just the same as that the cumulative of CF is less at x1 is greater than or equal to 0.98. So the cumulative of the first class at x1 is at least 0.98. Okay, so the 0.98 quantile of a standard normal is 2.05. In other words, it's 0.98 is 2.05 standard deviations above the mean. So that means, yeah, so I'll have to set I have to have at least 2.05, standard deviation is 4. What's that? The standard normal, yeah. So so my standard normal has to be at least greater than or equal to 2.05. Or x1 has to be 2.05 for standard deviations above the mean. And the standard deviation is 4. So 4 times 2.05, it's 8.2. 8.2 plus 16 gives us 24.2. Yeah. It's the 0.98 quantile.
So that's the corresponding one in the standard normal is
2.05. Yeah. So in the standard normal, it's 2.05. So that means I need to get 2.05 standard deviations above the mean. All right, and that's 24.2. Now the second constraint, because of the way because of the way I wrote it, go back here. All right, so this is the cumulative distribution at x1 plus x2 of the sum of these two random variables. Well, the sum of two normal random variables is also a normal random variable. So I just have another normal random variable, which is their sum. And now the sum has the mean that's the sum of the means. And since I said they were independent, the variance is the sum of the variances. So the variance is 16 plus 48. That's a 64. So when I take the square root, it's 8. So the second constraint is just that the distribution function of the sum of the first and business class at x1 plus x2 is at least 0.95. And that says, so the sum has a mean of 46. 0.95 of the standard normal is 1.645. So I have to be 1.645 standard deviations above this mean for the sum. And that means that x1 plus x2 is at least 59.16. So now I've converted those probabilistic constraints into deterministic constraints. And now this is precise because it's just saying that exactly these constraints would satisfy my conditions. Now if I restricted it to integer variables, then of course these would have to be integers. But assuming the normal distribution, then these constraints give me an equivalent representation. Okay, so often you can do this. You can just write down basically the cumulative distribution and then come up with deterministic constraints from that. Okay, so here's another one where it takes a little bit more work. So here's I'll use another one of these problems again, location problem. Okay, so this is, again, where you put down locations, and then if they're close enough to a place of demand, then you can serve that demand. And if they're too far, then you can't serve that demand. But the additional thing I put in here, think of it as like ambulances. I put ambulances at different places around a city, and I want to be able to pick up patients, pick up people who request the ambulance in any place in the city. But if one of those ambulances is already picking up another patient, then they're not available. So what I want is that there's a high probability of a free ambulance being available to pick up any of the patients. So I want to have a minimum probability of not having an ambulance available for any of the patients. So it's not just the location, but their availability that I want to put into the model. Okay, so I'll put the ambulances in sites. So think about this. Think of this as putting ambulances in different places. I'll put the ambulances into different sites, again, 0, 1, and let's say there's a cost for each of the ambulances that I put in each of these sites, and then these clients. So the clients would be the patients. Well, if I can respond to them quickly enough, so there's a certain time, if they're too far away, then I can't get the ambulance there in time, and the patient, I could lose the patient. So I can't have a patient too far away from one of the sites. Right, let's say that this is the distance between each of the potential locations, and then this would be the set of eligible sites. So for every client or every patient here, this would be the set of sites that could get an ambulance to that patient in sufficient time that we would be able to save the patient, say. Okay, so the deterministic model is just what I had before in that example, where I minimized the cost of making some installations. In that case, I was able to essentially put in extra ambulances later. Here, I'm not going to allow extra ambulances, but what I want is that this probability of having someone who can respond to a call is going to be high. Okay, so for the stochastic model, I want that the probability that at least one emergency unit is available to be greater than or equal to some value alpha. So this would be like, I want to make sure that there's a 95% chance that everyone can be served by a free ambulance. And I have, as a parameter, Q is going to be the probability that that an ambulance is not available. So Q is the chance that they're busy at any one point in time. So I'm not modeling that, but I'm going to say that there is a certain probability that ambulances are occupied, that they're taking care of other patients. So Q is a probability that none of them is available. And what I want is to come up with a constraint such as the probability that at least one unit from the eligible sites is available. Okay, so this would be the probability if I sum over, this is basically the sum of 1 up here. If I sum over all the sites that are would be available for a given patient, the sum over all those possible sites, this would be the probability that there was no ambulance available. So if I take Q is that one site doesn't have availability, and then I multiply it by all the sites, it's like Q to the power of the sum of all those sites. So now if I introduce X here, this is 0 or 1 whether I open a site or not, then the probability that I can satisfy, the probability that I can serve the patient is 1 minus the probability that I can't. So it's 1 minus Q to the power of the number of sites that are open. And that has to be greater than or equal to alpha. Or another way to write it is then Q to the sum of all these sites is less than or equal to alpha. Now I can take the log on both sides, and then I get that when I take the log on both sides of the sum of the xj's less than or equal to the log of 1 minus alpha, or sum of the xj's times the log of q is less than or equal to the log of 1 minus alpha, or the sum of the xj's is greater than or equal to the log of 1 minus alpha divided by log q. And I may as well make it an integer, so I'm making it an integer here, because these have to be integers, so this should be an integer as well. So this is an equivalent representation. So now I've taken what was a probabilistic constraint, and I have transformed that constraint into a deterministic constraint here. So again, we have an equivalent form. So in both of those cases, I can take the probabilistic constraint and then just modify it, and I get an equivalent deterministic linear program. Or, yeah, in this case, linear program. Okay. So you can often do this with chance constraint programs, but there are some issues with them. And so here's one of these issues about this value of information. And the idea or the principle that people sometimes think it violates is this principle of information that if I have more information, I should always be able to make a better decision. So it should always give me higher value to have more information. So that should be an axiom, that more information is always worth more than less information. Okay, so if we believe that more information always gives us a better decision than less information, or that the expected value of perfect information is always greater than or equal to 0, that seems to be a standard. It should be a standard axiom of information or decision theory. Okay, so here's the sort of paradox, and it was in a paper by a man named Blau. There were a set of papers that debated this back and forth, all of which appeared in the Journal of Management Science in the 70s. So Blau's paper said, well, suppose, let's consider this probabilistic constraint. Suppose there is a situation where my demand is either 0, 90% of the time, or it's 1 10% of the time. And what I want to do is to minimize the amount that I order, subject to a constraint that I have sufficient capacity for the demand 90% of the time. Well, if it costs anything for that order, then the optimal solution is 0, because 90% of the time the demand is 0. So the optimal solution to the original problem has a value of 0. I should optimally order nothing, and then 90% of the time I will be able to satisfy the demand. 10% of the time I don't, but the constraint doesn't include that at all. It's just probability greater than or equal to 0.9. Okay, now, what he said was, well, what happens if I have perfect information? Suppose I knew the demand, and I still have to satisfy the demand 90% of the time. If I knew the demand, but I still have to satisfy it 90% of the time, then I have to satisfy it. I have to do it because I know it. So it's 100% of the time I know what the demand is. So that means if I had perfect information, well, yeah, for the 90% of the time when demand is 0, I'd order nothing. But for the 10% of the time when the demand is 1, I have to order 1. Otherwise, I can't satisfy this constraint. So the problem with perfect information has either value 0 with probability 0.9 or value 1 with probability 1. So with perfect information, the expected value is 0.1. But the value without perfect information was 0. So he says the expected value of perfect information in this case is negative. You're worse off to know the actual demand than to not know it. And that's a contradiction. So he says this model doesn't make any sense because it contradicts this basic axiom that that more information should be better. Perfect information, of course, should be better than anything in terms of information. The same thing you can devise examples like this for robust optimization, for sample information. You can devise it. If I thought of Xi as the set of demands such that the probability is greater than or equal to 0.9, I would, again, just end up with 0. So the robust formulation would give me the same kind of result. Okay, so it seems like this is saying that there's some kind of contradiction in these models, that there's a contradiction of some sort of basic principle. But yes, it was. But what people debated is, but no, you can't really use the same. You can't use the same kind of model when you have perfect information as when you don't have perfect information, because when you have perfect information, it doesn't make any sense to have like a probabilistic constraint because you've already realized what the uncertain parameters are going to be. And the problem without perfect information, it still may. You're just not. You're kind of comparing apples and oranges. That this is a different problem from the problem where you have the perfect information. I can't really express them in the same way, and I'm not. It's not really measuring the same thing. Whoops. Okay. So. Really, your utility, in this case, you can't condition, you should condition your utility on the information level. The utility shouldn't depend or shouldn't be different depending on the information level. So it could be that with no information, it's okay that 90% of the time you satisfy the constraint and 10% of the time you don't. But with complete information, it's not okay to do that. And so, depending on your information level, it's not, you can't really make comparisons because utility does depend on your level of information. So it's not really, it's not always easy to make these comparisons. So I don't know that you can always make comparisons the way they did in that previous example. The other thing is, it's like there's something else that's going on. If I'm saying that it's okay that I satisfy the constraint just 90% of the time, I'm saying that it's okay to throw away this 10% of the time when the demand is 1. So in other words, I'm saying that it would be all right to just have a 0 over here, because to be consistent with the 90% up here. So it would be consistent to say, well, if I'm saying it's okay to just do this 90% of the time, then the consistent way to solve this problem would be that it's 0 here and 0 down there, because I'm still satisfying it 90% of the time from what I did at the beginning. So we could think about it that way. The other way to think about it is that sometimes information may not be, there may be correlations between the information and what environment you're actually in. So it could be that you gain information, but your competitor gains information, and your competitor now is going to make things worse for you. So the fact that gaining information may not be good for you in the long run because you may give that information to your competitor. And so giving information to a competitor, so that axiom that more information is better as long as it doesn't affect anything else about your utility or about the environment. But if information affects something else about the environment, then that's not necessarily always better. So having more information may not always be better if it changes your environment. And in this example, it's kind of changing your environment. It's saying, oh, now I know what the demand is, so maybe now I can't ignore it. So it's changed your environment. It's changed what the actual values are going to be. So by changing your environment, either because there's a competitor or because something else has happened, more information may not always be better. So that's a second way to think of as resolving this paradox. Okay, there's some other kinds of paradoxes like this, but in this case, I think it's not. It's not fair to say that I have to meet this demand if I said I didn't have to meet it up here. So either the problem has changed completely. In other words, my utility is actually quite different in this environment than it was in this environment. Either my utility has changed, or if my utility hasn't changed, then I can make that a 0. So either way, it kind of resolves the problem. So I either resolve the problem by saying, that's not the right objective if I maintain consistency, or, well, the information has also changed my objective, and therefore I shouldn't expect the value of information to increase. Okay. All right. Yeah, so as I said, it may not correspond to axioms of choice in this general case. there's also this is kind of another reason why these may not always give you consistent results. Like this value at risk. Value at risk is again the smallest value such that the probability in the tail is alpha. So it's like the negative of the alpha tail of the distribution. So value at risk has, I mentioned that it has a property that it may not be convex in the values x. So for example, suppose, so x is like my uncertain outcomes in the future. And so suppose it's possible that I lose $1 with probability 0.5%. Otherwise, I'm where I am. Let's say I made a loan. Either the loan gets paid back and I end up at 0, or it doesn't. And with a 0.5% probability, and I've lost it. And let's say there's a separate loan, and it also has a probability of 0.5% that's -1, and then a 99.5% probability of being paid back. Okay, so if I just take x1, the 99 percentile bar is 0, because 99% of the time I'm at 0. The 99% of the 99% var of x2 is also 0, because 99% of the time the worst I do is 0. However, suppose these are two events, like suppose I'm actually making loans to two competitors, and either one of them gets in trouble or the other gets in trouble, but never both. So either this one is going to have some problems, and then the other one's going to survive, or the other one has some problems and this one survives. So in other words, suppose these are disjoint events. So these two losses are actually disjoint. When I add them together, then I have a 1% probability of losing one, because these are two disjoint events. So it's possible that the var, the 99% var, this is again loss because it's a negative up here, that the amount that I could lose with probability of 99%, when I put them together, that's 1. So separately, they're 0, but putting them together, because they're disjoint events, it makes it a 1. So when things are correlated, this value at risk doesn't have convex property. It can't take convex combinations of these that would have to be 0. But here, I take some combination of the two, and I get 1. So clearly, var doesn't have convexity as a property, and this is again a thing where it would violate some of those axioms that we would see. And the question is whether it is consistent, whether it's consistent to say, okay, it's 99% is okay here at 0, but it's not okay here. It could be that you would say, yeah, that is consistent, because I just want to make sure that 99% of the time I save myself. But it violates convexity. So it does violate convexity here. Whereas those other things I mentioned before, CVAR and any coherent risk measure, will never have this property. It will always satisfy a convex relationship. Okay. Now, so this is just an illustration that sometimes the feasible regions may not be convex. And here's an example. So I have this example. Okay, so A is 1 and -1. And then h is either 0 and minus 1, or 2 and minus 3. And again, what I want is that the probability ax greater than or equal to h, where both these things are random, is greater than or equal to alpha. Okay, so if you look at this first h, so it's x times 1 and then minus x, greater than or equal to 0 and minus 1. Okay, and all right, so this just says x is between 0 and 1. Right, and then if I do the other one, it's x and minus x, 2 and minus 3. So this one says x is between 2 and 3. Okay, so if each of those occurs with probability 1/2, so if this has chance 1/2 and this has chance 1/2, then probability 1/2, well, with probability 1/2, I satisfy the constraint if x is either between 0 and 1 or between 2 and 3. So the feasible region is disjoint even. It's not just non-convex. It's 0, 1, and 2 to 3.
What is alpha here?
If alpha's a half. Yeah. Alpha's equal to a half. So then I'll have these two disjoint regions. So that's, I'll mention in a minute. Now, I could try to do something like have a 0, 1 variable that would say I'm either in this region or in that. But, but in general, I'm going to have to deal, in general, I would have to deal with these non-convex regions. In fact, disjoint regions. Okay, so the way to get around this is to use this property called quasi-concavity. And quasi-concavity says that the probability of any convex combination of sets, so this would be the probability of all these random variables, or the probability of convex combination of this random variable and this random variable being in some set. The probability of any convex combination of sets is at least the probability of the two sets independently. So this is the concave version of quasi-convexity. That the probability operating on the convex combination of the two is now greater than or equal to the minimum of the two. If it was convexity, it would be less than or equal to the maximum of the two. Yes, yeah. So can they satisfy it? Yeah. So many probability functions satisfy this. Yeah. So, for example, normal distributions will satisfy. Yeah. Quasi-concavity implies log concavity. Right. So I'll show if A is fixed and H is Q concave. So if the distribution of H is Q concave, then it's a convex. Then you always have a convex region. And there are some other cases, which I'll mention, when you have convex regions. So the good thing about having convex regions is that then there's a way in which you can generate a deterministic, there is a deterministic equivalent. So there should be a deterministic equivalent for any of these distributions, well, when we have these convex properties. So for example, if A is fixed and H is the only thing that's random, so if H here is the only thing random, then we can come up with a finite representation. So, or we can come up with a linear representation or a deterministic representation. Okay, so let's look at. This is just to say what to do. Yeah, I mentioned about doing the binary variables. So if there are disjoint regions like this, and you can split up those disjoint regions into separate ones, like HIX greater than or equal to GI. And then you'll say, okay, X can be in any of those disjoint regions or any of those possible regions. It doesn't have to be disjoint, just they're all convex. So I separate the regions that give me feasibility into convex sets. So I separate them like here. These are two convex sets. I separate them into convex sets, and then I say, okay, so if X is in one of those convex sets, then I'm sure that the probability is greater than or equal to alpha. So I need that X has to be in one of those convex sets. So I'll have a condition that says there are some binary variables such that HIX plus some big number times 1 minus each of the binary variables is greater than or equal to GI. And the sum of the binary variables is 1. So that means if one of these is 1, I have to satisfy it. So I have to satisfy one of those constraints. And then I let the binary variables determine which of those constraints is going to be satisfied. Or it could be, sometimes what we might do is, let's say we just have a set of samples. So we have a set of samples of the A's and a sample of the H's. And I want to make sure that I get a certain probability out of these samples. So I want to get out of n samples, probability has to be alpha. That means that the sum of the samples that are satisfied, so the sum of the z's that have to be 1, is at least alpha times the number of samples. So I can, for sample representation, I can also represent samples without having to do find a deterministic equivalent. I can represent it with samples, but I'll have to use integer variables. So in general, you need integer variables to, well, in general, you'll need integer variables to represent these models. But with samples, you don't have to assume any properties. I don't have to assume anything about the distribution. I'm just going to say, I'll just take some samples. I don't have to know what the distributions are. I can still satisfy it with a given probability. And the expense that I pay for that is that I have to deal with integer variables. So, but that's all you have to do with. You just have to deal with the integer variables to work with that. Okay, let's. Okay, so here's the result for quasi-concavity in. This is the case where A is fixed, so the constraint matrix here is deterministic, and the only uncertainty is represented in the random right-hand side. And what we want is that the feasible region, where the probability that this is satisfied is at least alpha, we want that that's a convex set. Okay, so again, let's say H is the set where the x's satisfy the constraint. So H is the set of x's that satisfy. H is the set of x's where x satisfies the constraint. All right, so this is distribution over h's. Okay, so this is the set of h's where ax is greater than or equal to h. Okay, let's say there are two x's, and I'm going to combine them. All right, so I'll take a convex combination of two x's. And then I'll have an H1 in H of the first set, and an H2 in H of the second set. So what I want is that I have a convex, I want that this feasible set is convex. So if x1 and x2 are both feasible, in other words, if the probability of h of x1 is greater than or equal to alpha, and the probability of h of x2 is greater than or equal to alpha, what I want to show is that the probability of x of lambda, a x of lambda greater than or equal to h, that probability is also greater than or equal to alpha. Okay, so what I'll do is to look at each of the h's, look at any of the h's that are in these sets. So I'll take a convex combination of any of the h's that are in these two sets. So I'll take lambda h1 plus lambda h2. The set of those h's, and what should be true about that? Well, h1 is again less than or equal to ax x1, and h2 is less than or equal to ax x2. So lambda h1 plus 1 minus lambda h2 is less than or equal to ax lambda. So that says, well, let's see. So h of x lambda, so ax lambda has to be greater than or equal to the linear combination of this. So that means that these h's must be in x lambda. So h of x lambda has to include all of the combinations of h at x1 as well as h at x2. So it's all convex combinations of those two things. And now we've got, so this is where we use the quasi-concavity. So that says the probability of this set is greater than or equal to the probability of this convex combination of these sets. But I know that each one of these had probability that was at least alpha, so that's got to be greater than or equal to alpha. Yeah, this is. Yeah. Both of them are greater than or equal to alpha. So both of them are greater than or equal to alpha. Yeah, so it's greater than or equal to the minimum of these two, and they're both greater than or equal to alpha. So then it must be convex. And then, well, this is just for closure. So closure, we just use h is less than or equal to x nu, have some subsequence, and then we have, okay, so the probability h at any limit of that subsequence is going to be greater than or equal to the lim sup of the h's in this set, and that's greater than or equal to the probability of this is greater than or equal to the probability here. Yeah. I think this is Fatou's lemma. Yeah, Fatou's lemma. Yeah, yeah. About sets. Yeah. Yeah, it's a little bit beyond that. But so this is just for closure. Convexity is the most important thing here. Okay, now let's look at some other conditions to get. So the nice property we want to get is this Q concavity. So here's a nice property for it. So if f is the density of a continuous probability distribution, and if f to the power minus 1 over m is convex, so if this is convex on Rm, then this probability measure is quasi-concave. Okay, so this is a good property because what it says is something like this exponential here. Any distribution that has, so if f of x is equal to e to the minus L of x, where this L of x is a convex function, then f of x to the minus 1 over m is e to the m L of x. So anything that has a representation like this, where L of x is convex, yeah, m is positive. Anything that has a convex exponent on the exponential is going to be quasi-concave. Well, this family of distributions, like if L of x is, I guess it doesn't have to be. Yeah, so if L of x is like x squared over 2, that's a normal distribution. If L of x is just x, that's the exponential distribution. The beta distribution fits in this family. Dirichlet distribution fits in this family. So all of these are going to be quasi-concave. So this entire family of distributions are all quasi-concave. All right, so here's another result. So if A is fixed and the components of H are stochastically independent and they have logarithmically concave probability measures, then effectively, yeah, so then I just want that AI, each of these AIs times X has to be greater than or equal to H. Well, they're each independent, so I need that the probability that each one of them is satisfied is just the product of all of them. But that's a probability that each one independently satisfies the constraint. And I can add all of those together. So the feasible region ends up being just take the log of the cumulative distribution at each one of the left-hand sides of the constraints and make sure that that sum is greater than or equal to log of alpha. This is just the same as saying that the probability that each of these, or the product of all of them being less than or equal to alpha, and then taking the logarithm of that. Okay, so again, we get, so this would be the deterministic representation of probability X greater than or equal to H, in this case where the components are all independent. Okay, now there's some additional results for the normal distribution. However, there's no result that basically works for any kind of distribution on A and H. So each row of the matrix A, and then the column H. So I take the vector of all the rows, and then the column H. And I assume that they all have a joint normal distribution. And it's it's a particular kind in that there's a common covariance between every pair. So if I take the covariance, matrix between any two rows of A, I can write it as some R associated with the two rows, Rij, times this common covariance matrix. So we have this common covariance matrix which links every pair of these together. And if I combine any of the rows with the right-hand side, it also has it's just a multiple. The covariance of that is just a multiple of this common covariance matrix. So as long as, if I have a structure like this with common covariance matrices, then again, I can write it out as if it was one big normal distribution multiplied by a set of matrices. So you can turn this into basically a single normal distribution. So if you work it out, it's like this matrix, it's going to be this matrix R, and then this vector S, and then it's just going to be combinations of that, and a set of independent normal distributions. So you just need the n1 plus 1 independent normal distributions to generate everything. And everything can be written in terms of them. That's what having this common covariance matrix means. Okay, so basically you can rewrite it in terms of n1 plus 1 independent normal distributions. And then you can do all the same things that you would do with a single normal distribution. You can do it with this, and you have convexity as long as alpha is greater than or equal to half. And let's see, there's one other here, which, this one's just that if there's just a single row, and if h is 0, so this kind of trivially using this relationship here, then again, it just goes down to a single normal random variable, or normal random vector, where it has mean with the mean of the row, and then the covariance matrix is just the covariance of the different components of the row of A. And then, as I say, you just turn it into a single normal distribution. So it's just like A1 times X is your normal distribution greater than or equal to H. And so A1 times X that's just another normal random variable, which has a standard deviation of X1 times this matrix C1 times X. So in this case, you just it's just saying it's a probability AX greater than or equal to H. Here it's just H1. And this is normally distributed, and this is just another normal. This is just mean A1 bar, or A1. This was A1. A1 bar times X, and then the covariance is X transpose C1X. So I've just written it as another normal random variable. Yeah, so it's just another normal random variable. Okay, so I said that there was this controversy about chance-constrained programming because of the value of information. And there were, there was at least 3 papers in management science that sort of debated this. But in some ways, you can always get the same answer from a chance constraint problem as you can from a problem with recourse, the two-stage problems. So this is just to show you how that's always possible. So chance constraint problems, as I said, well, here I said T instead of A, but think of it like this. Probability that I have to satisfy these constraints is at least alpha. If I just have a single constraint like that. And let's say just H is random, so if just H is random, then this is a convex constraint. Then this is equivalent to saying, well, the probability distribution of H, cumulative probability, is alpha. If the cumulative probability is alpha, then it's just saying that Ti has to be at least as great as that quantile. So this is the alpha quantile of the H distribution. And then there's an equivalent constraint that says, okay, I just would satisfy this, solve this problem, minimize C times X, subject to AX equals B. These are the first stage constraints. And then for the second stage, I'm just saying that whatever my transformation of X is into that second stage, it has to be at least as great as these HI variables. Okay. Well, so I'll get a solution to this problem. And this was this example comes from a set of notes by Shail Parikh. Do you know this name, Parikh?
Parikh.
Yeah. And he did a set of notes that they never got published. But he has this set of notes from a class he taught at Berkeley. And they're never published, and they're just kind of handed around. So anyway, this comes from his sets of notes. I think it's Shailendra Parikh. Yeah, S. Parikh. Statistician. Yeah, statistician. So you have this optimal solution. So X, let's say X is the primal optimal solution, and the dual variables are lambda associated with the A and pi associated with the T. So each of the rows of T. And so we have, again, duality. C transpose times the optimal X is equal to B times the optimal lambda and H times the optimal pi. So then I can set up a problem where if pi star is 0, I just have Q is 0. If pi star I, its ith component is positive, then I'll set up a Q that's pi divided by 1 minus alpha. If I solve this recourse problem, I get the same solution. I'll get the same X star. X star that solves this problem is the same as the X star that solves the other problem. So there's an equivalent representation here. I could either I can either do it as a chance constrained, or I can do it as a recourse problem. And so in the same thing, I can do it vice versa. If I start with a recourse problem, I can come up with a chance constraint problem. So there's, for each, now, it may not be obvious what the equivalent problem is, but there is usually an equivalent representation. I mean, almost always. There's an equivalent representation. So you can almost always have either a reliability constraint or a recourse function, a recourse action that you can take. Okay, now I'm going to give you a couple of results. This one is interesting because I think the proof is interesting. So one thing you could do is you could say, well, I have to satisfy this set of constraints with a certain probability, but maybe you don't know the distribution all that well. Or it's an online problem, like a machine learning problem, and I just get samples. So I'm trying to see whether my samples, I want to be able to ensure that a certain fraction of the people whom I observe are willing to buy a product. And I'm going to come up with conditions that are satisfactory for all of them. But I only have some samples of this random parameter. Well, I could set up my model such that I satisfy the constraints for those samples. And then the question is, if I satisfy the constraints for these samples, is that enough to satisfy this probabilistic constraint? So if I have a set of samples, and let's say the samples are drawn independently, if I have a set of independent samples and I satisfy all of those, what's the chance that I've satisfied the constraints in general with a given probability? So if I satisfy all of them in my sample set, let's say they're new samples, what's the chance that I've satisfied all of them in general with a certain probability, with probability alpha? And the result here is that for any epsilon, for any value of epsilon that's between 0 and 1 minus alpha, and for any value of this parameter beta that's between 0 and 1, if I satisfy all these samples, and the number of samples is at least, this is the dimension of the problem, if it's at least the dimension of x divided by epsilon times beta. So both epsilon and beta are going to make me need more samples. So if I'm, whoops. So if I have a sufficient number of these samples, then I'm going to satisfy this constraint. And I think it's probably this constraint, alpha minus, epsilon is sort of determining my alpha. If I satisfy this constraint, then I satisfy this constraint with probably at least 1 minus beta. So in other words, I can make 1 minus beta be, so I satisfy, so epsilon is anything up to 1 minus alpha. So in other words, I can put 1 minus alpha in here. And then I can satisfy the constraint. In other words, I'll have alpha reliability in my constraint with confidence level 1 minus beta. So I'm 1 minus beta confident of meeting the constraint alpha % of the time. Okay, so here's the setup of this. Let's suppose that the chance of choosing exceeds such that one of the, for a given x, the chance of choosing a C for a given x such that I don't satisfy the constraint, let's suppose that is V. So V is like the probability that I'm not satisfying the constraint. So V is the chance that x does not satisfy the constraint. And let's suppose my x new has satisfied all of the constraints with new samples. So I've satisfied all the constraints with new samples, and what I want to look at is, well, what's the expected value of not satisfying, of not satisfying any constraint, and how likely is it that I didn't satisfy a constraint? So what's the expected value that I didn't satisfy the constraint for an x new that solved a sample problem? All right, well, what I'm going to think of is, suppose I take that x new and I draw a bunch of other samples. So I'll draw nu plus 1 other samples. And suppose that for each one of these draws of these samples, I have another xk nu that's solved for all of them except for one. And I'll just leave out the kth of these. So I'll leave out the kth of the samples. And if it didn't satisfy the kth one, then I'll let this new k be 1. So new k is 1 if I take a draw of these samples. I satisfy all of them, but if I didn't satisfy the kth one, then I put that in as this new k. Okay, so the expected value of new k is like the expected value that's like the chance that one of these samples, the same as up here, it's the chance that one of these x's that solve for all the samples is not going to satisfy all the constraints. So I must have that this is true. And the other thing is that it must be true. Well, I can't. It must be true that in n dimensions, whenever I solve a problem, I've solved this problem in n dimensions, and I have a bunch of these constraints. If I solved it with all of them, removing, I can only have n constraints that are actually going to be changed. So there's only n, if I solved it with all of them, there are only n constraints that I could violate with any one when I remove one of them. So there's at most n of these that would change if I removed one. Because it's at my x, let's say this is x nu plus 1. It's going to be at most at the intersection of n constraints, because it's at best at an extreme point. And in n dimensions, extreme points are determined by n different things. So there's at most n that I could possibly remove. So in other words, I'll never get more than n out of this entire set. So the expected value over all of them is at most n out of the nu plus 1 values that I have. So the chance of the expected value of having any one of them be violated out of the nu plus 1 possible ones there is at most n over nu plus 1. And that's because of this extreme point result, that there's at most 2 in n dimensions that I could remove and that it would change the solution. So there's at most 2 that I could violate by dropping one of them. So that gives me that expectation is at most nu over n plus 1. So now from Markov's inequality, the probability, well, the probability that v of x nu is greater than any epsilon is less than or equal to, we did this before, less than or equal to the expected value of that v divided by epsilon. As I said, this is less than or equal to n divided by nu plus 1. So this probability that the number of violations is greater than alpha is less than or equal to n divided by nu plus 1 times epsilon. So if nu plus 1 is greater than or equal to n over epsilon beta, then this whole thing is less than or equal to 1 over epsilon times n over n times epsilon times beta. The epsilons go away, and now I've got beta. So the probability of a violation is less than or equal to beta, or the probability of satisfying it is at least 1 minus beta. or my probability is of a violation is less than or equal to alpha anyway. So the probability that I've satisfied all the constraints is at least 1 minus alpha, or 1 minus epsilon, which is greater than or equal to alpha. Okay, this is just an example of when you might use this. So for example, you might have a large portfolio of loans, each of which could default. So all of them, and so the portfolio of loans could be, if they're consumer loans, it could be in the thousands. And it would be very hard to find out what's the probability that thousands of these loans are not going to give me at least a return of H after all the defaults. So this is, A here is basically 0 or 1 for whether the loan gets paid back. Each of the loans is worth B over N, so this would be this is the expected, or this is the value of the portfolio after their default. So what's the probability that the value after the default is at least some given value? I want that to be greater than or equal to alpha. And in general, this would be very hard to calculate. But if I have enough observations, so if I get lots and lots of observations of loans, and I make sure that I satisfy this constraint on all those observations, then I can get, I can bound what's the probability that all the loans are, in general, are going to satisfy with this probability alpha. There's some other kinds of bounds. I also mentioned this Chebyshev inequality. So there's a one-sided Chebyshev inequality, which is the probability being greater. This is random variable minus its mean is greater than or equal to some value A. So the probability that random variable minus its mean greater than or equal to some value A is at most the variance divided by the variance plus that value A squared. So this probability is at most sigma squared divided by sigma squared plus A squared. All right, now, so we can take this, I'll just transform this a little bit. So I take that AIX greater than or equal to H, and I'll write this in terms of, well, so this has a constant part C0 and then a random part C transpose plus, or a part that's associated with H that's going to be C0, and then part that's associated with A, that's this C, and that's greater than or equal to some set of constants. And then I can transform X again. Let's say C has a given covariance matrix, and then I can get, basically substitute for in the Chebyshev inequality for the variance, and for the right-hand side, and we can rewrite AX greater than or equal to H just like this, and then we'll get, we'll just use the X transpose CX, where this was the variance of those random variables. Oops. Okay, so we can get bounds this way as well. So we can use the Chebyshev inequality, and that gives us a bound. Yeah, so if X satisfies, this would give, this gives us actually. Yeah, so the probability of AX is AX greater than or equal to HI is greater than or equal to alpha, then this should be true. So this would be, this would give you a lower bound. So if I satisfy this constraint, that's like a relaxation of this, because I know that all the things that satisfy this are going to imply this. So this gives me a larger feasible region, so I get a lower bound. But then I can get an upper bound by applying basically the negative of the previous results. So this, if I want to get an upper bound, this condition down here gives you is going to imply that you get this constraint up here. So if I put in this condition, then that gives me an upper bound, and if I put in this condition, it gives me a lower bound. But I can use either of those to get bounds as well. Yeah, so other things you can do is just to require some of the sample values. So that previous one, I required all of them. Sometimes you can require some of them. And you can also refine these bounds. This, what I call the Boole-Bonferroni inequalities. So these are inequalities that actually give you results on these probabilities as well. So the idea is just to take it's generalizing the Boole or Boole-Bonferroni inequality, which is just that the probability of the union of a set of a bunch of sets is less than or equal to the sum of the probabilities of those. And so the fact that the probability of the union less than or equal to the sum, and then what you can do is take the probability of the union minus the probability of the intersections. That's going to be a lower bound. And you can get upper and lower bounds and sort of put them together. Well, there's a result from Sanoff that says I can look at the complements of all these sets. The probability of the union of all the complements can be lower bounded by a relationship between the sum of these complement probabilities and their intersection. So I have to just do, this stands for the intersection, so I have to do the sum of these probabilities and the sum of the intersection of these probabilities, and I can get a lower bound on the union. So this is like a bound on the possibility of a violation somewhere. So the complement is a violation. This is the probability of a violation. Yeah, and this is just a result that puts that together, saying, okay, so probability AX less than or equal to H is something like, well, this is just giving you a bound. So there is so lambda gives you the bounds. So lambda is between 0 and 1. So you get a lower bound when lambda is 0 and an upper bound when lambda is 1. So I know that this probability is always between, again, this is just doing the probabilities one constraint at a time or two constraints at a time. And then I can get upper and lower bounds. So you can do upper and lower bounds this way. Okay, so this was all about chance-constrained problems. And things to remember is that they may seem inconsistent, but it depends on really how you describe the model and how information affects the objective. So it's more about the interplay between the information and the objective. What you want to do with chance constraints is to come up with equivalent formulations. You want to come up with convex problems, so use quasi-concave distributions to get that. There is generally a formulation, always a way to go back and forth. So there's always a way to go back and forth between chance constrained and these recourse models. And you can use these approximations either to get lower or upper bounds in these problems, and you can use samples to get those bounds as well. Okay, so any questions? Yes? Yeah, so yeah, it depends on, so the user has to determine a confidence level, so you have to say what's your, then the feasible, it makes the feasible region small, yeah. Okay, all right, thanks.